Second, performance of the solar cell. Next, how to increase efficiency of the solar cell. Next, we will discuss the organization of the solar cell. In the organization, I will discuss the following topic: photovoltaic effect. In photovoltaic effect, especially electromagnetic spectrum, band gap, and solar cell junction. Solar cell junctions help to increase the efficiency of the solar cell. But there is one problem in that is lattice mismatching. Next, we will discuss about that how to remove lattice mismatching problem in solar cell. Next, we will discuss the solar cell spectrum AM node, AM 1.5 spectrum in solar cell. Next, we will discuss the current voltage curve, in which I will explain how to find out the efficiency of the solar cell. To simulate the solar cell in Silvaco TACD, you must know about user-defined photo generation. There are different types of user-defined photo generation. I will discuss in this presentation user-defined beam, user-defined arbitrary photo generation, exponential photo generation, tabular photo generation. Next, we will discuss the most important parameter of the solar cell, that is how to define optical properties of the material, in which I will explain setting single value for the refractive index, setting a wavelength dependent refractive index, and the quantum well absorption. Next, we will discuss how to simulate solar cell in the Silvaco TACD. To simulate, you must know about the solar spectra, solar optical propagation model, solar cell extraction, and the indium gallium nitride material. We are using the indium gallium nitride material in the Silvaco TACD tool. I will discuss about this material in detail. For example, band gap of the material. The most important property of the indium gallium nitride material, it is a radiation hard semiconductor material. Next, we will discuss the challenges you will face to use indium gallium nitride material in Silvaco TACD tool. Next, we will discuss how to simulate indium gallium nitride material in Silvaco TACD. Next, we will discuss how to increase the efficiency of the solar cell by increasing the number of junctions in the solar cell. First, I will discuss the single junction solar cell. Next, we will discuss the dual junction, 3 junction, and the quad junction solar cell. And the last but not the least, I will give some recommendation for the future research of solar cell. Let's start with the solar cell. What is solar cell? The foundation of all the solar cell is the basic PN junction diode, or simply a diode. A diode used in electrical circuit is covered with an opaque insulation in order to prevent light from the interfering with its operation. A solar cell is a diode that utilizes incident light to generate an electrical current. If you are using the silicon diode, then the energy radiated in the form of heat. But if we are using some specific material like indium gallium nitride, indium gallium phosphide, then the energy radiated in the form of light. The color of light depends upon the material of the semiconductor. This presentation investigates the potential use of verticide indium gallium nitride as a photovoltaic material. Silvaco Atlas was used to simulate single junction solar cell, the dual junction solar cell, 3 junction solar cell, quad junction solar cell in this presentation. Each of the junction was made up of indium gallium nitride. The band gap of each junction was dependent on the composition percentage of indium nitride and the gallium nitride within indium gallium nitride material. Indium gallium nitride material is a combination of two materials. First one is the indium nitride and the second one is gallium nitride. How much we are using the indium nitride and the gallium nitride, it will depend upon the mole fraction. The finding of this research show that the indium gallium nitride is a promising semiconductor for solar cell use. Next, we will discuss the performance of the solar cell. One of the most important problems to solve in space solar cell design is efficiency. As efficiency increases, the required number of cells decreases to fulfill electrical power requirement. Solar cell efficiencies have improved over time by increasing the number of junctions in the solar cell. Each junction is capable of extracting energy from a portion of the solar spectrum. The inefficiency of solar cell due to high operating temperature presents a growing issue for the spacecraft industry. Currently, the problem is solved by accepting the manufacturer design and compensating for losses with solar arrays. A new path to improving efficiency is to use new photovoltaic material such as vertesite indium gallium nitride. Indium gallium nitride possesses a band gap range that can extract energy from a large portion of the visible solar spectrum. How it does I will explain in the next slides. By varying the composition of indium nitride and gallium nitride within indium gallium nitride, the band gap of this semiconductor material can be changed. What is the value of band gap of indium gallium nitride? It will depend upon the mole fraction value. The band gap range of indium gallium nitride matches closely the visible solar spectrum frequencies. Hence, a high frequency solar cell can be potentially developed by having several indium gallium nitride junctions. We can increase the efficiency of the solar cell by increasing the number of junctions. But if you are increasing the number of junctions, it will increase the weight of the solar cell. It will create a problem in the space solar cell junction. Many different factors affect solar cell performance. First one is the doping concentration of the semiconductor material, types of the material, thickness of the layer, lattice growth, and even the manufacturing process can influence a cell performance. The goal of this research was to investigate the efficiency of indium gallium nitride solar cell using the Silvaco Atlas TACD simulation software. Next, we will discuss the organization of the solar cell, in which first I will discuss the purpose of solar cell. The purpose of solar cell is to convert light energy into electrical energy. Light is made up of photons. Photons carry energy that is dependent on the color or wavelength of light. Electrical energy is generated when photon excite electron from the valence band into the conduction band in semiconductor material. Next, simulation software. Silvaco offers a suite of software programs that can act as a virtual wafer fabrication tool. Silvaco tool is actually a VWF, virtual wafer fabrication tool. We are using the material indium gallium nitride material. Indium gallium nitride is a semiconductor that has the potential to produce high efficiency solar cells based on the optical characteristics of indium gallium nitride. Simulations were performed using Silvaco Atlas tool. Next, we will discuss the photovoltaic effect. The photovoltaic effect is the process by which a solar cell converts the light energy into electrical energy, or simply we can say that the energy comes from the light into electrical energy. We know that light is made up of photons. The energy of these photons depend upon the color of the light. I have already explained that. The material that makes up of the solar cell determine the photovoltaic properties when light is applied. When light is absorbed by the metal, such as metal, photons provide the energy for the electron to move from the higher energy state within the material. Simply, if we are exposed to the material into the light, the electron present in the valence band to move towards the higher energy state into the conduction band, so that the excited electron, when returns to the original energy state, it will radiate energy. Next, in semiconductor materials, there is a built-in asymmetry or we can say that band gap. This allows the electron to be transferred to an external circuit before they can return to the original energy state. The energy of the excited electrons create a potential difference. This electromotive force directs the electron through a load in the external circuit to perform the electrical network or electrical work. Next, in photovoltaic cell, we will discuss the electromagnetic spectrum. Light is electromagnetic radiation. The frequency of light determines its color. Figure show the visible part of the electromagnetic spectrum. This is the visible part of the electromagnetic spectrum. So that the material having the wavelength in this range can be used in the solar cell. Figure show the visible part of the electromagnetic spectrum. Visible wavelength range from 390 nanometer, that is violet, to 780 nanometer, that is red color. The energy radiated will depend upon the wavelength of the light. If the wavelength of the light is about 390 nanometer, then it will be radiated in the form of violet color. If it is very high, is approximate 780 nanometer, then it will be radiated in the form of red color. The sun emits light from the ultraviolet, visible and infrared wavelength in the electromagnetic spectrum. Solar irradiance has the largest magnitude at visible wavelengths, peaking in the blue and the green color. Table show the approximate wavelength of various colors in vacuum. Red color has a wavelength of about 622 to 780 nanometer, and the orange color has the wavelength of 597 nanometer to 622 nanometer, and the yellow color has a wavelength of 577 nanometer to 597 nanometer, and the last one, violet color, has the wavelength of 390 nanometer to 450 nanometer. Next, we will discuss the band gap of the material. The band gap of the semiconductor material determines how the solar cell reacts to the light. Table show a small sample of the semiconductor band gap. This one table. The band gap of the silicon material is about 1.12 electron volt at 300 Kelvin. Germanium material has a band gap of 0.66 electron volt, and the gallium arsenide has a band gap of 1.42 electron volt, and the indium phosphide has a band gap of 1.34 electron volt at 300 Kelvin. The band gap of semiconductor material determines the wavelength of light that meet the requirement to generate electrical energy. The conversion formula between the band gap and the wavelength is this one. Wavelength is inversely proportional to the band gap, in which lambda is the wavelength in a micrometer, h is the Planck constant, c is the speed of light in vacuum, and Eg is the band gap in electron volt. 1 electron volt is approximately equal to 1.6 into 10 raised to power minus 19 joule of energy. In the case of gallium arsenide, the wavelength that corresponds to 1.42 electron volt is having the wavelength of 0.873 micrometer. Figure show the effect of light energy on different band gap. Figure helps visualize the concept of light absorption. When light has the energy greater than 1.1 electron volt, the silicon solar cell generates electricity. Light with less than 1.1 electron volt of energy is unused. Similarly, light with having the energy greater than 1.43 electron volt excite the outer shell electrons of the gallium arsenide solar cell. And finally, the light having the energy greater than 1.7 electron volt is useful for aluminum gallium arsenide photovoltaic material. Simply, we can say that if the light energy has energy less than 1.1 electron volt, then it has no use. If the light energy has energy greater than 1.1 electron volt, the silicon solar cell, the first one, it will generate the electricity. when the light energy have greater than 1.43 electron volt, then it will be passes and it will be radiated energy. Simply, if you are using the aluminum gallium arsenide material, then the light energy must be greater than 1.7 electron volt to radiate energy, or we can say that generate electricity. Next, we will discuss about solar cell junctions. The discussion in the previous section discussed the effect of light energy on different band gaps. Treated individually, each of the photovoltaic materials from previous figure would act as a single junction solar cell. In the last figure, we will discuss about the single junction solar cell having the material of silicon, single junction solar cell having the material of gallium arsenide, single junction solar cell having the material aluminum gallium arsenide. I have considered individual junction to generate electricity. However, to increase the efficiency of the solar cell, multiple junctions can be created. For example, in the last figure, the top junction would be made up of aluminum gallium arsenide. This junction would absorb light energy greater than 1.7 electron volt. Any unused photons would be filtered to the next junction. The gallium arsenide junction would then absorb the photon having the energy greater than 1.4 electron volt. The remaining photon would be absorbed by the silicon junction. In the second paragraph, I have explained that if we are using the 3-junction material, the inner junction is silicon material, outside of the silicon is gallium arsenide junction, and the outer shell is made up of aluminum gallium arsenide. We are using the triple junction solar cell. Although the above paragraph describes the basic of multi-junction solar cell, such device may not produce the desired results due to lattice mismatch. The next section covers the basic of lattice mismatching. If you are using the 3-junction solar cell, then there is a problem of lattice mismatching. In the next slide, we will discuss how to remove the lattice mismatching problem in the multi-junction solar cell. Lattice mismatching, or we can say that lattice matching. Semiconductors are 3-dimensional in their cell structure. The simple cubic structure serves to illustrate the concept of lattice and is presented in the figure 3, that is the simple cubic lattice structure. Figure 3 shows that each side of the cube is represented by the letter A. The separation A is called the lattice constant. Each semiconductor material has a lattice constant and it having a different value. Therefore, when creating multi-junction solar cell, the lattice must be matched. The alloy indium gallium phosphide is composed of X parts of the gallium phosphide and 1 minus X part of the indium phosphide. Therefore, indium gallium phosphide is represented by indium mole fraction 1 minus X, gallium mole fraction X, and the phosphide. Gallium arsenide has a lattice constant of about 5.65 angstrom, and the gallium phosphide has a lattice constant of about 5.45 angstrom, and indium phosphide has a lattice constant of about 5.87 angstrom. The goal is to create indium gallium phosphide with a lattice constant that matches that of gallium arsenide. The formula to find X is given as: we have to find out the value of X that will help to match the indium phosphide and gallium phosphide junction lattices. This is the formula: lattice constant of gallium arsenide, lattice constant of gallium phosphide into mole fraction X, lattice constant of indium phosphide multiply by the mole fraction 1 minus X. By solving this equation, you will find out the value of X. The value of X, that is mole fraction. That value give the exact value of mole fraction that will help to match the lattice of different material, indium phosphide and gallium phosphide in this example. By solving the above equation, you will find out the value of X is 0.52. Then this means indium 0.48 mole fraction and gallium phosphide having 0.52 mole fraction and has lattice constant of 5.65 angstrom. A rough approximation of this resulting band gap of indium gallium phosphide is given as follows. Energy band gap of indium gallium phosphide is equal to mole fraction x band gap of gallium phosphide plus 1 minus x mole fraction into band gap of indium phosphide. This equation yields a band gap of 1.9 electron volt for indium gallium phosphide. Therefore, a dual junction solar cell of indium gallium phosphide having the band gap of 1.9 electron volt and the gallium arsenide having the band gap of 1.4 electron volt can be built. By using this equation, you will find out the multi-junctions material band gap. If you are using the indium gallium phosphide junction, then you can find out the band gap of this material if you know the value of mole fraction, that is x. In this example, the value of x is 0.52. If you solve this equation, you will find out the band gap of indium gallium phosphide material is about 1.9 electron volt. Next, we will discuss the solar spectra. Solar spectra we are using in this example is AM node spectrum. The location of the solar cell affects the input solar radiation spectrum. A solar cell on Mars receives a different spectrum than a solar cell on a satellite that orbits Earth. The energy received outside Earth's atmosphere is approximately 1365 watt per meter square. This is the meter square. This spectrum is called air mass zero. The full form of AM is air mass zero spectra. Terrestrial solar cells have to deal with the attenuation of the solar spectrum due to Earth's atmosphere. The solar spectrum is called air mass 1.5. The purpose of this presentation, AM node is used during simulation. Next, we will discuss the current voltage curve of solar cell spectrum. A typical solar cell current voltage curve is presented in the figure 4. You can see that simple current voltage curve used in efficiency calculation. The solar circuit current occurs when the voltage is zero. That is the point. This is the short circuit current that will occur when the voltage is zero. This is the highest absolute value of the current. Next is the open circuit voltage. VOC is the open circuit voltage that will occur when the current is zero. At that point, the value of the current is zero. This is the highest voltage. The dimensions of the large rectangle, this one is a rectangle in the figure 4, are determined by the open circuit voltage and the short circuit current. Since power is determined by the product of current time voltage, current multiplied by the voltage, the maximum power point occur at this point. When the power is maximum, that is the maximum power voltage and the maximum power current. The calculation of the solar cell efficiency are as follows. This one, maximum power in the solar cell is the IMP and the VMP. This is the Q point, operating point or maximum power point. That is this one. You can find out the maximum power in the single junction solar cell. This is the graph of the anode current and the cell voltage for the single junction solar cell. If you are using the multi-junction solar cell, you will find the number of graphs having different band gap. I will discuss the multi-junctions in the next slides. In the single junction slide, if you find out the value of the efficiency, you must know the maximum power point, VMP and IMP. You can find out the maximum power point, P maximum, in which FF is the fill factor. It is defined as the ratio of maximum power point to the short circuit current into open circuit voltage, ISC and VOC. If you are putting the value of P maximum, that is the VMP and the IMP, you you will find out the fill factor. If you find out the value of the efficiency of the single junction solar cell, then the P maximum divided by P input, you can easily find out the value of the efficiency of the single junction solar cell. The fill factor measures the squareness of the IV curve. Next is the electrical output. A solar cell is a PN junction photodiode. In order to obtain the current voltage characteristics of the solar cell, the dark current needs to be subtracted from the photo-generated current. I is the finalized current, IL is the light current, and the ID is the dark current. The dark current must be subtracted from the light current to find out the final value of the current in solar cell. The dark current is the current through the solar cell when bias is applied in the dark. Graphically, I have shown the electrical output of the single junction solar cell. This one is the IL, this is the light current, this is the dark current. I have subtracted the value of dark current in the light current and find out the final value. In the previous slide, I have shown the current voltage characteristics of the single junction solar cell is like that. This one I talking about. The final value of the current after subtracting the dark current. Next, to simulate the solar cell in the Silvaco, you must know about the how to define the photo generation method. The first one is the user defined beams. Second one, user defined arbitrary photo generation. Third one, exponential photo generation. And the last one, tabular photo generation. Next is the user defined beams. Theoretically, a number of ways to specify a beam of arbitrary shape exist. The one chosen in Atlas aims to allow you an easy interface with the optical system design software. Atlas treats the ray bundle specified in a file as one beam. You need to set the input file name on the beam statement as a value of the input rays parameter. The input rays must have the following format: number of rays, beam 1, 2, 3, 4, 5, 6 and so on, and the number of changing parameter 1, 2 and 3. Ray parameter, first one you have to define the ray number. Next the parameter 1 value, parameter 2 value and the so on. Next you have to define the next ray number. Number of rays stands for the total number of rays specified in the file. It should be the same as the last ray number in the table. Next, number of changing parameter. Number of changing parameter means it will gives the total number of ray parameters given in the table. Most often, some parameters are the same for all the rays. For example, wavelength or ray power can be the same. In this case, there is no need to keep the table column for this constant parameter. Instead, you can set the parameter directly in the beam statement. Next, number of changing parameter is equal to the number of column in the table, not counting the first column number, that is the ray number. Parameter 1, 2 and 3 and so on are the numerical codes of the parameter. Their order specify the order of the column in the table. Numerical codes correspond to the flowing parameter. Those you are defining the numerical codes parameter 1, 2 and 3, it will consist of, first one is the x coordinate of ray origin in device coordinate system. Second one is the y coordinate of ray origin, and the third one is the z coordinate of ray origin. Fourth one, ray angle phi in xy plane, either for x-axis it will be 0 or 90 for the y-axis. Ray angle theta in xz plane in 3D only you have to define 04 angle 04 along x-axis and 94 along z-axis. Next is the ray polarization angle relative to the plane of incidence. Next, ray relative power. Next, you have to define the parameter of ray wavelength 8 number. 9 is the ray area in micrometer square in 3D or thickness micrometer in 2D. The first column of the table where ray parameter are specified listed ray number in the ascending order. It must be start from the 1. The last ray number should be equal to the number of rays. Often it is the case that ray parameter change continuously from ray to ray. The parameter for the ray 1 must be different from the parameter of the ray 2. If you are defining the ray number from 1 to 10, you must to define these parameter from 1 to 9. 1 for the different value and the 9 for the different value. You can choose a particular also. You can define only the 2 and 3 parameter. First one parameter, fourth parameter, sixth parameter and the ninth parameter. It depends upon the needs in the solar cell. In the next slide, I will take an example to understand this concept to you. Linear approximation is used for the omitted ray based on the value of the parameter given in the table. This is best illustrated in the following example. And the first one is the number of rays, that is 21. Here the number of rays 21. Next you have to define the number of parameter. I have defined we are using only the 3 parameter out of 9. I have explained in the last slide. I am choosing the 3 parameter and the order of the parameter column x coordinate 1. I have defined the first one, that is the x coordinate 1. This will x coordinate 1 and the 4 parameter ray angle phi in xy plane. Second parameter is the angle phi and the third parameter is the relative ray power, that is 7. The rays from 2 to 10 are specified using linear interpolation with end value given by the ray 1 and the 11. The rays from 12 to 20 are also defined. Similarly, the shortened input is equivalent to the following. Next, I have defined the number of rays 21. I have defined the 3 parameter. 3 parameter are the 1, 4, 7. This is the ray number 1 and the first parameter x coordinate. First parameter, the x parameter of origin plane, that is 0.0, angle is 60 degree and the relative ray power is 0.2. Next 2 for the x coordinate of origin plane 30 and the angle phi is 63 and the relative ray power is at 0.28. You can note down that from the ray number 2 to 10 there is a linear change of 30 in the x coordinate of origin plane, 3 in the angle phi and in the relative power is 0.08. There is a linear change for the ray number 1 to 11 and the ray number 12 to 20 also has the linear change. You can note down that from 300 x coordinate of origin plane to 600 with a difference of 30. So that we can define these rays from this method as well as from this method. Next we will discuss the user defined arbitrary photo generation. An option exists from the U to define the photo generation rate. A C interpreter function written into a text file can be supplied to the program using the f.radiate parameter of the beam statement, which I have defined a file in the C interpreter function that will consist of all the parameters of the beam rays. If you want to call this file, you have to use this syntax f.radiate parameter in the beam statement. For example, if a file myoptics.c was developed using the template C interpreter function supplied, it can be referred by using. Then the beam number 1 f.radiate. I am calling my previous defined file in the C interpreter function. The name of the file is myoptics.c. Any file defined in the C interpreter function have the extension of .c. Next we have to define the solve function for the beam 1 and the beam 2. The file myoptic.c return a time and position dependent photo generation rate of the program. This return file is multiplied at every node point by the value of beam 1. With the option, you override all the other parameters of the beam statement and the material refractive index. Next is the exponential photo generation. Another option is available if distribution of photo injected carrier is uniform, linear, or has an exponential dependence on depth. Use the photo generate statement to specify the desired dependence on depth along a line segment. The x origin, y origin, x dot n and y dot n parameter set the coordinate of the beginning and end of the line segment. The default value corresponds to the top left and bottom left corner of the device. Other parameters, constant, exponent, factor, linear and radial, specify the photo generation rate according to the following formula. This is the formula, in which L is the distance along the line segment from the origin point and R is the radial distance from the segment. I am not using the exponential photo generation in my code. If you want to go deeply about the exponential photo generation, you must follow the Atlas manual how to define the photo generation in the exponential photo generation method. Next we will discuss the tabular photo generation method. You may also specify the photo generation rate as a function of location through a simple tabular interface. This is the tabular interface I have defined: 1E22, 1E22, 1E20 and 1E20. This is often useful of importing data from some other generic optical propagation tool. The value of the photo generation rate are contained in a file. You specify the file name on the file.photogen parameter of the beam statement. The file contains ASCII value of photo generation rate in units of per second per cubic centimeter. These samples are made on a regular mesh in X and Y rastered in increasing value of X and then Y. The value are space separated in X and separated by carriage return in Y. The spacing in X and Y in micron are specified in the dx.photogen and dy.photogen parameter of the beam statement. If you are specifying the dx photogen and dy photogen parameter in the beam statement, you are specifying the value of x and y in micron. You can specify the origin of photo generation in micron using x0.photogen and y0.photogen parameter of the beam statement. Simply, if you are defining the value of origin of the photo generation, you have to start from the x node dot photogen and y node dot photogen parameter in the beam statement. If you do not specify the x node dot photogen and y node dot photogen, then the origin will be assumed to coincide with the minimum x and y coordinate in the device structure. For example, the beam statement is like that: beam x node photo generation is used for the origin of the photo generation in x direction, y node photogen is used for the origin of the photo generation in micron using y node statement. Dx dot photo generation is used for the defining the spacing in x micron or specified parameter. For example, the beam statement might read: beam x node photogen is 0, y node photogen is 0, x node and y node. I have already told you about that. This is the origin of the photo generation. Dx photogen 1, dy photogen 1. I am calling the generation table using file.photogen statement. The content of the file named generation table might be simply 1E22, 1E22, 1E20 and 1E20. In this case, the photo generation rate is uniform in the x direction, range from 0 to 1 micron, but varies linearly between 1E22 to 1E20 in the y direction. Next slide will explain the simulating photo detector. It will be used in P injection diode, LEDs, organic FET. This section describes technique simulate photo detector. This section applies to the simulation of any of the following device: PN, PIN, photodiode, avalanche photodiode, Schottky photodetector, CCDs, photoconductors, optical threads, and optical trigger power device, in which you have to understand how to define optical source, how to identify an optical beam, origin plane of the optical beam for 2D optical source, origin plane of the beam for 3D optical source, and the reflections, in which you have to also understand the specifying periodicity in the ray trace, defining luminous beam intensity in 2D, defining luminous 3D beam intensity, monochromatic or multispectral sources, and the solar sources. I am not explaining about this in my presentation because it can make my presentation so boring. If you want to learn about these photo detector simulating method, you have to go through the Atlas manual. For detailed study, you have to follow the Atlas manual to understand how to simulate photo detector in Silvaco TACD Atlas tool. In this slide, we will discuss how to define optical properties of the material. For ray tracing, the complex index of reflection of the various material regions in the structure must be specified. For many of the more common semiconductor and insulator, there are built-in table of index versus wavelength. You can specify the index of the material lacking responsible default complex index of reflection, in which I will explain you how to set single value for the refractive index, how you can set a wavelength dependent reflective index, and the quantum well absorption. Note that you can add the index.check parameter in the solve statement to understand how to print out the reflective indexes being used for that by step. The indices are only printed when you perform the ray trace at the first reference to a given beam on the solve statement. First, we will discuss setting single value for the reflective index. The real dot index and the imaginary dot index parameters of the material statement can be used to set the real and the imaginary indices of a specified material, region, or number of regions. For example, this statement: material air reflective index real dot index is 1 and the imaginary dot index is 0 would set the index of all the parameter regions composed of air. The statement material region 1 will set the real value of the reflective index 1 and the imaginary value of the reflective index is 0 would set the index for the region number 1, and the statement material real dot index 1 and the imaginary dot index 0 would set the index of all the regions. It's so simple to set the value of the real value and the imaginary value of the reflective index in the Silvaco Atlas tool in the material statement.
Next, setting a wavelength dependent reflective index. The preceding example set the complex index of reflection for a material regardless of the wavelength. The previous method I have discussed, in which I have not considered the wavelength. In the next method, I will consider the wavelength. This is probably advocate for monochromatic source. For multispectral simulation, the index of reflection should be modeled as having a dependence on the wavelength. There are two ways to define the wavelength. First one is the ASCII file input. The first way is to specify index versus wavelength in a file. This is a text file, NK file, that contains order triplets of wavelength, real index, and imaginary index. The first entry in the table is the number of samples. If you set the index.file parameter of the material statement to the name of the index file, you can use any name. For example, if you are defining the index file for the indium gallium arsenide, you can use indium gallium arsenide dot text dot nk file. If you are defining the index file for the graphene material, you can define graphene dot txt or graphene dot nk file. If you set the index.file parameter of the material statement to the name of the index file, the linear interpolation from this table will complete to obtain the index of reflection as a function of the wavelength. A valid index file is shown below, in which 2 is the number of rows, and the first column showing the wavelength, second showing the real part of the reflective index, and the third one is the imaginary part of the reflective index. In the first column, the real index is 2.0, imaginary index having the value of 0 would be used for a wavelength of 0.5 micron for the first column. If you are talking about the second column, the real index is 2.0, imaginary index is 0.02, would be used for a wavelength of 0.6 micron for the second column. You may also use ASCII file input to input real index and complex index independently. You can assign index.real to the name of an index file containing ordered pairs representing the wavelength and real index of reflection. Similarly, you can assign index.imaginary to the name of an index file containing ordered pair representing the wavelength and imaginary index. You can use a single file with .nk.txt file, or you can use two files. First file is for the index.real, which contain the wavelength and the real value of the reflective index, and the second file is the index.imaginary. It will consist of imaginary part of the reflective index and wavelength. By default, the unit of wavelength are in micron, and the index is represented by the real and the imaginary part. You can change the interpretation by including two character codes as the first non-comment line in the file. The following table explains these interpretation. ASCII index file interpretation codes. If you are using none of the code, then the wavelength in micron, real index and the imaginary index. If you are using AE in the code, then the energy in electron volt, real index and absorption coefficient per centimeter. If you are using the code AN, then the wavelength in nanometer, real index and the absorption coefficient in per centimeter. If you are using the AM code, then the wavelength in micrometer, real index and the absorption coefficient in per centimeter. If you are using the NM code, then the wavelength in nanometer, real index and the imaginary index. If the code is electron volt EV, then the energy in electron volt, real index and the imaginary index. C interpreter function. The second way to specify index file versus wavelength is by using the C interpreter function. The syntax is in which I have already designed a file and saved in the program, and I'm calling this file with the help of material statement using the syntax f.index. Material name silicon using the syntax to call the file f.index, and the file name is myindex.c. The file myindex.c is an external file conforming to the templates supplied by the program. It returns wavelength dependent real and imaginary indices. And the third one is the SOPRA database. You can choose to use reflective index data from the SOPRA database. To do this, you must specify the appropriate index file from the table B40. You can see in the Atlas manual on the SOPRA parameter of the material statement. Simply, there are three methods to define a wavelength dependent reflective index. And the first one is the ASCII file input, that is named as .nk file, .txt file, that is represented by index.file statement. And the second method is C interpreter function, in which I have saved a file. I am calling the file with the syntax f.index. And the third one, we can use the value of wavelength, reflective index, real and the imaginary part in Sopra database. You can simply write the statement Sopra equal to that file name, for example, indium gallium arsenide.nk file. For more detail, please go to the B40 table on the Atlas manual. This is the Atlas manual. This is the Sopra database. The Sopra database is a collection of complex refractive indexes of various materials, sometimes as a function of temperature and wavelength. To access this data, you should specify the file name from the table. You can use any file name from the table using with the Sopra parameter in the material statement. Simply you have to define, so SOPRA is equal to, you can call any file from the Sopra database. 7059, the first file is 7059.nk file, and the AGNK, you can call any file that is represented in the database. If you are designing, if you are using any other material that is not mentioned in the B40 table, then you have to define their NK file by using the previous method. Next is the outputting wavelength dependent complex index for the Tony plot. The complex indices of reflection can be written to file suitable for display in Tony plot by specifying the file name root without extension of out.index parameter of the material statement. The files created will use this root appended by the n.log for real indices and k.log for the imaginary indices. For indices input by the Sopra database, the root will be appended by nn, this is n capital and small n dot log and capital N hyphen k dot log, where n is the sequence number from 1 to any, to accommodate the capability of the Sopra format to allow dependence on the composition fraction and temperature. And the last one is the quantum well absorption. The complex index of absorption can self-consistently include the effect of quantum confinement. To enable this model, first you should specify Q-well parameter on the region statement of regions where you want to consider quantum confinement. This will simply force the calculation of bound state energy in the region. Second, you need to specify ABS on the same region statement to inform the simulator that you want to use the confined state energies in the calculation of the complex index of reflection. Next, you can either use the confined band gap represented by the difference between the lowest conduction band bound state energy and the highest valence band bound state energy in the calculation of complex index of reflection using the C interpreter function f.nkeg. This is specified by f.nkeg parameter on the material statement. If you do not specify the f.nkeg parameter, the model will use the negative of gain function for the quantum well. In this case, you should also specify the proper gain function parameter on the model statement. If you want to include the quantum confinement effect, you must define the quantum well absorption Q well in the region statement. You also must define the ABS syntax on the region statement. To inform the simulator, we are using the quantum confinement statement in the calculation of complex index of reflection. If you want to include the quantum confinement effect, you have to define the statement f.nkeg using the C interpreter function. in the material statement. But if you don't specify the f.nkg parameter in the model statement, then the model will use negative value of gain function. So that you have to must include the f.nkg parameter on the material statement. Next is the simulating solar cell. The luminous simulators are well suited to the simulation of solar cell. Particularly, the variety of fast optical propagation model in the combination of capability of the device simulator in the Atlas framework makes accurate solar cell simulation a possibility. The following paragraph focus on the problem and solution, specify the simulation of solar cell, in which first I have considered the solar spectra, second solar optical propagation model, and the third one is the solar cell extraction method. How to define the solar spectra in the Atlas manual. Luminous and Luminous 3D provide built-in definitions of solar spectra for AM0 and AM1.5 conditions. To specify these spectra, define AM0 or AM1.5 on the appropriate beam statement. These spectra consist of numerous samples, and we therefore suggest you carefully consider subsampling. The following is an example of how you might define the beam statement for analysis of AM1.5 conditions with subsampling. In our code, I am using the AM node spectra statement. In this example, I have mentioned the AM1.5 spectra. Beam number 1, AM1.5 spectra have the wavelength start from the point 3 and the wavelength end at 1.2 and the wavelength number 50. Here we are choosing to simulate AM1.5 conditions sampled between 0.3 micron and 1.2 micron at 50 samples. We do not have to worry about sampling the many peaks and valleys in the solar spectrum, as it is automatically integrated into each subsample. The subsampling affects only the number of wavelengths for which the propagation model is calculated, not the integrated intensity. Next is the solar optical propagation model. The choice of optical propagation model for your purpose depends largely on the nature of your solar source device. In some cases, you may want to apply several of different models to compare the results against measurement for your particular analysis. In all cases, accurate knowledge of complex index of reflection of material comprising the solar cell versus wavelength is key in accurate light propagation modeling. In the proper light propagation modeling, you must know about the complex index of reflection of the material consisting of a particular wavelength. That is the main task to operate the solar cell modeling. Luminous and Luminous 3D provide built-in defaults for most material of importance to solar cell technology. See section B1.3 in the Atlas manual. If you have a little knowledge of optical properties of the material in your solar cell, or if you are less interested in the propagation problem, you may choose to simply define the photo generation rate using the C interpreter function f.radiate. This function allows you to directly specify the photo generation rate as a function of position of the device. The following illustrate the use of f.radiated C interpreter function for constant generation rate. If you don't know about the optical properties of the material in the solar cell, or you are not interested to go complex propagation problem, so better you have to choose the f.radiate statement in the beam for constant generation rate. First, you need to simply identify the C function defining the generation rate to the simulator. This is done in the input deck on the beam statement using the f dot radiate parameter as follow. Beam number 1 f dot radiate is equal to solar library LIB. If you define the ray in this manner f dot radiate dot solar library, you don't need to define any NK file in the material statement. You can see in the Atlas example, most of the experiment are using f dot radiate syntax parameter to define the beam in the spectra. Next is the solar cell extraction. Here we will describe how to extract the most common figures of merit for the solar cell. These extraction methods are solution strategy placed in your input deck after defining the device structure, physical model, and the optical source as described in the previous section. Typically, the first step in the solar analysis is to illuminate the device. You can turn on the illumination by assigning the beam intensity on a solve statement as follows. Sol B1 is equal to 1.0. This is the beam intensity. Here we assign a value of 1 sun to the intensity of the optical source indexed as beam number 1 B1. As we had assigned AM here we assign a value of 1 sun to the intensity of the optical source indexed as number 1 beam 1. As we had assigned air masses 1.5 on the beam statement, this corresponds to the standard test conditions. In some cases, we may encounter convergence difficulties and may need to ramp the light intensity as shown in the figure. Solve V1 0.01, 0.1 and 1.0. If you are finding the convergence problem in your code, then you must have to define the light intensity into the ramp function. Simply we can say that you are increasing the intensity value from 0.01 to 1.0. You may also choose to assign the beam intensity to a value greater than 1 to simulate solar concentrator effects. Since we have not yet assigned any bias voltages, the current in the runtime output corresponds to the short circuit current. Till now we have not defined the bias voltage corresponds to the short circuit current. Next we will talk about the material used in the solar cell, that is indium gallium nitride material. First I will discuss about the band gap of this material. Indium nitride has fundamental band gap was approximately 0.77 electron volt at room temperature. Since gallium nitride has a band gap of approximately 3.4 electron volt at room temperature, then indium gallium nitride can have a band gap of ranging from 0.77 electron volt to 3.4 electron volt by changing the percent composition of indium gallium within indium gallium nitride. The value of the band gap of the indium gallium nitride material will depend upon the mole fraction X. The following formula provide an approximation of indium gallium nitride band gap. Eg is the band gap, X is the mole fraction, 3.42 X. 3.4 electron volt is the work function of gallium nitride and 0.77 electron volt band gap of indium nitride, in which 1.43 is the Boeing parameter B. Indium nitride having the 1 minus X concentration and the gallium nitride having the X concentration. One of the property of indium gallium nitride material is it is a radiation hard semiconductor material. Radiation hard material are essential for space applications. When compared to other gallium arsenide and indium gallium phosphide, indium gallium nitride is able to withstand a great amount of radiation. Indium gallium nitride retains its optoelectronic properties at radiation damage doses at least 2 orders of magnitude higher than the damage threshold of the material, gallium arsenide and gallium indium phosphide, currently used in high efficiency of solar cell. This indicates that the indium gallium nitride is not only potentially a high efficiency photovoltaic material, but it is also able to withstand the harsh space environment. But there is some challenges in the indium gallium nitride material. There are some significant issues that currently prevent indium gallium nitride from being used as a photovoltaic material. As of this writing, no PN junction has been built. The PN junction is essential to create photodiodes. Indium nitride has the highest electron affinity among all semiconductors. Hence, indium nitride has a tendency to be n-type. It is much more difficult to build p-type material with indium nitride. However, evidence of p-type doping in indium nitride and indium gallium nitride has been reported in the previous paper using magnesium. This is a step in the right direction in this area of indicates the creation of indium gallium nitride PN junction.
Next, we will discuss the simulation of indium gallium nitride in Silvaco Atlas tool. Solar cell will first design as single junction. The most popular photovoltaic materials has been silicon due to its abundance and relatively low cost. The maximum efficiency of polycrystalline silicon is approximately 19.8%. Commercial silicon solar cell have a maximum efficiency of approximately 13%. Improvement in efficiency can be obtained in a single junction solar cell by using gallium arsenide. Monocrystalline gallium arsenide has a maximum efficiency of approximately 25.1%. Earlier we are using the silicon solar cell. We know that the silicon having the property of abundance. Earlier we are using the silicon based solar cell due to its abundance and low cost. The polycrystalline silicon solar cell have an efficiency of 19.8%, but when we move to the commercial it will be reduced to 13%. And the efficiency of the solar cell can be increased by changing the material. If you are using the gallium arsenide, then the single junction solar cell efficiency is increased to 25.1%. By designing dual junction solar cell, the efficiency can again be improved. A dual junction solar cell with gallium phosphide as the top junction and the gallium arsenide as the bottom cell will have an efficiency of 30.3%. Increasing the number of junctions makes the cell more complex in design and the gain begin to diminish. Although it will increase the efficiency of the solar cell, but the gain start reducing. Triple junction cells have efficiency of approximately 31% and the quartz junction have the efficiency of approximately 33%. It is expected that the 5 and the 6 junction solar cell have the efficiency of 35%. This simulation uses indium gallium nitride as photovoltaic material in a simulation. With its full spectrum characteristics, the efficiency of indium gallium nitride has the potential to surpass the previous result. By using the indium gallium nitride material, you can increase the efficiency to up to 40%. Single junction solar cell. Figure shows a graphical representation of the single junction solar cell. The thickness of the emitter is about 0.01 micrometer and the doping is 10 raised to power 16 per centimeter cube. The thickness of the base is 3 micrometer and the doping of the base is again similar to 10 raised to power 60 per centimeter cube. The first step is to develop single junction solar cell. The gap energy and the elementary optoelectric parameters used in the simulation for the junction. Indium gallium arsenide having the mole fraction X is 0.20. Indium gallium arsenide having the mole fraction 0.57 and the indium gallium arsenide having the mole fraction 0.68 and 0.78 are detected in the table. If we are changing the mole fraction of the indium gallium arsenide, it will automatically change the band gap of the material. In case of when the mole fraction having the value of x is equal to 0.20, the band gap energy is 2.66 electron volt. It is 2 point, not comma. This is the point. When the value of mole fraction x is equal to 0.57, then the band gap energy is reduced to 1.60 electron volt. When the value, as you increasing the value of the mole fraction, it will reduce the band gap energy. When the value of x is equal to 0.68, the band gap energy is reduced to 1.31, and the value of when the x is equal to 0.78, the band gap energy is reduced to 1.10 electron volt. If you want to find out the value of this band gap energy, you have to follow the previous equation as I have explained about how to find out the band gap in the previous slides. This is the single junction solar cell, this is the emitter, this is the base. First of all, you have to find out the optical data in the form of dielectric constant when the value of mole fraction is 0.20. The dielectric constant was then converted into index of reflection and extinction coefficient K using a MATLAB script. I had mentioned the MATLAB script at the end of the slide. First, you have to convert the optical data in the form of dielectric constant. If you don't know how to convert, I will mention one paper at the end of the presentation in which you can understand how you can change the optical data into the dielectric constant. After convert into dielectric constant, you have to design a .nk text file in which n is the index of reflection and k is the extinction coefficient. It can be done by using the MATLAB script. The band gap and the optical data were entered into the input deck. How to get the NK file, I will explain through MATLAB in the end of the presentation. The simulation ran in the Silvaco atlas. From the log file, the current and the voltage were extracted. This is the log file you will obtain when you run the single junction solar cell. I have run the program 4 times with a different band gap of energy. First for the 1.10 electron volt, then 1.31 electron volt, then 1.6 electron volt, and the last one 2.66 electron volt. In the single junction case, each of the cells had air masses 0 as the input spectrum. Figure 6 show the current voltage curve for single junction solar cell. Figure 6 shows the current voltage curves of 4 single junction solar cells. The current voltage curve pattern corresponds to the empirical finding of other multi-junction solar cell. Typically, the cell with the highest voltage has the lowest current. You can note down in the figure. The cell with the highest voltage is around 2.225 have the lowest current, and the lowest voltage around 0.75 has the highest current. Table 1 will show the short circuit current and the open circuit voltage, fill factor, and the efficiency of the single junction solar cell presented in the figure 6. The efficiency shown in the table 1 indicate that a high efficiency single junction cell with X mole fraction indium gallium nitride material has good prospects. A 24.32% efficiency compared favorably to the single junction gallium arsenide efficiency of 25.1%. The indium gallium nitride cell simulated can be optimized by changing the thickness of the junction and changing the doping level, adding a window, a back surface fill BSF, and a buffer can also help in improving the efficiency results. These improvements can be subject to the future research. When you are using the mole fraction x is equal to 0.2, the short circuit current is 17.613 milliampere per centimeter square, and the open circuit voltage is 2.23. In the previous figure, you have noted down that if you are increasing the open circuit voltage, then the short circuit current is reduced. If you are increasing the value of mole fraction from 0.20 to 0.278, the open circuit voltage start reducing and the short circuit current start increasing. When the value of X is equal to 0.20, the fill factor is 83.72% and the efficiency is approximate 24%. If you are changing the mode fraction to 0.57, the efficiency is reduced to 12.35%. When you increase the mode fraction to 0.68%, the efficiency is reduced to 10.52%. And if you are increasing the mode fraction to 0.78, the efficiency is reduced up to 8.19%. Next is the dual junction solar cell. Figure 7 show a graphical representation of dual junction indium gallium nitride solar cell. The thickness and doping level remain identical to single junction case. From the discussion in the single junction solar cell section, it should be clear that the best combination of indium gallium nitride band gap is 2.66 electron volt and 1.60 electron volt, since they have the highest efficiency. So that we are using the two junction, one having the band gap of 2.66 electron volt and one having the band gap of 1.60 electron volt. It should be noted that for this simulation, the AM node air masses 0 spectrum was provided for the top junction when the value of mode fraction is 0.2 in the indium gallium nitride material. It has the band gap of 2.66 electron volt. The bottom junction having the mole fraction of 0.57 of indium gallium nitride material and it has the band gap of 1.60 electron volt. Receive the air masses 0 spectrum minus the spectrum absorbed by the top cell. Note that the current level of the top two cell is identical to the dual junction case. However, the current level of the bottom cell is lower than the single junction case for the same concentration. Similarly to the dual junction case, the current of the overall current voltage curve is limited by the individual junction with the lowest current voltage curve. The voltage are added accordingly since the three junctions are in series. Figure 8 shows the current voltage curves of the dual junction solar cell. Note that compared to the figure 6, the current voltage curve of electron band gap 2.66 electron volt stayed the same, while the current voltage curve of electron band gap 1.60 electron volt had a current drop. This current decrease was expected because the input spectrum was diminished by the top cell. Earlier we are using these band gap independently, 2.66 electron volt and the 1.60 electron volt. But when we are using both band gap in the dual junction, when we are using both band gap in a dual junction, then the current voltage curve of electron band gap 2.66 electron volt has no change, but the electron gap of 1.60 electron volt had a current drop. This is due to the input spectrum was diminished by the top cell. This one is the electron band gap for green one for the electron band gap 1.60 electron volt and the red one for the electron band gap for 2.66 electron volt, and the top junction has no change, but the bottom junction has a small drop in the current value because it is covered by the top junction. When we are using both together, you will get the curve shown in the black, and this is the point of the maximum power. This is the power point of Bm and Imp. In the dual junction solar cell, we are using the top material having the mole fraction of 0.20 and the bottom junction having the mole fraction of 0.57. It has the short circuit current is approximate 17.1111 milliampere per centimeter square and the open circuit voltage is about 3.38 volt. By using the previous fill factor formula, you will find out the value. You will get the value of 83.25% and the efficiency of the dual junction cell is increased to 35.58%. Since the junction are in series in dual junction solar cell. The overall current voltage curve is limited in current level by the IV curve with the lowest current. This voltage are added accordingly. There is a significant increase in the efficiency from single junction solar cell to dual junction solar cell. Indium gallium nitride solar cell. This improvement alone should be enough to continue to pursue the development of indium gallium nitride solar cell. Next is the 3-junction solar cell. Figure 9 shows a graphical representation of 3-junction indium gallium nitride solar cell. Thickness and doping levels stayed the same as the single and the dual junction cases. From the single junction solar cell discussion, the 3 most efficient solar cell were selected, having the band gap of 2.66 electron volt, 1.60 electron volt and 1.31 electron volt. Now in the 3-junction solar cell, the top cell indium gallium nitride having the mole fraction 0.20 and band gap 2.66 electron volt received the air masses 0 spectrum. This cell indium gallium arsenide having mole fraction 0.57 and the electron band gap 1.60 electron volt received the air masses 0 spectrum minus the spectrum absorbed by the top cell. The cell having the mole fraction 0.68 having electron band gap 1.31 electron volt received the air masses 0 spectrum minus the spectrum absorbed by the 2 top cell. This is the diagram of simple 3-junction indium gallium nitride solar cell. It is important to note that the current level of the top 2 cells is identical to the dual junction case. However, the current level of the bottom cell is lower than the single junction case for the same concentration. Similarly to the dual junction case, the current of the overall IV curve is limited by the individual junction with the lowest IV curve. The voltage are added accordingly since the 3 junctions are in series. In the 3-junction solar cell, the red one is the electron band gap of 1.60 electron volt and the green one having the band gap of 1.60 electron volt having the same value as in the dual junction case. The current level of the last cell is lower as compared to single junction case for the same concentration. The overall current voltage curve is limited by the individual junction with the lowest current voltage curve. The voltage are added accordingly. Since the 3 junctions are in series, this is the overall 3-junction solar cell characteristics black one. This is the maximum power point in which you will get the value of VMP, maximum power voltage, and the maximum power current for 3-junction solar cell. In case of 3-junction solar cell, the increase in efficiency from the dual junction solar cell to 35.58% to 38.90%. The modest increase in the efficiency can be attributed to the drop in short circuit current from 17.11 mA per centimeter square to 14.12 mA per centimeter square. However, the increase in the open circuit voltage from 3.38 volt to 4.27 volt ensured that the efficiency would increase. From the table, you can note down that we are using the 3-junction solar cell, the top layer having the mole fraction of 0.20 of indium gallium nitride material, 0.57 for the second and the 0.68 for the third. It will reduce the short circuit current from 17 to 14.12 and increase the open circuit voltage, but it will maintain the efficiency to increase from 35 to 38.90%. Last one is the quad junction solar cell. Figure show a graphical representation of a quad junction indium gallium nitride solar cell. Thickness and doping level remain the same as the single, dual and 3-junction cases. Spectrum input follow the pattern of dual and 3-junction cases. As expected, the current dropped for all the cases where AM node had been reduced by the top cell. Top cell has the same current voltage characteristics, but the remaining three cell has reduced in the current voltage characteristics as compared to individual junction solar cell. Figure shows the current voltage of quad junction solar cell. Note down the current voltage characteristics of top three cells are identical to the three junction cases. This is red, green and blue. And the fourth and the inner junction cell having reduced in the current voltage characteristics. And the last cell having the energy band gap of 1.1 electron volt. And the overall 4 junction solar cell having the characteristics of this black one, and this red point given the power maximum power point BMP and the IMP to find out the fill factor and the efficiency. From the table you can note down that the short circuit current is start reducing continuously and the open circuit voltage increases, but it will maintain the efficiency to increase up to 41.69%. The top cell having the mole fraction of 0.20 and the bottom cell having the mole fraction of 0.57, 0.68 and last one is 0.78 mole fraction. For completeness, efficiency calculation of the quad junction solar cell are provided below this one. We can find out the value of the maximum voltage and the maximum current from this maximum power point. This is a BMP. It has approximate value of 4.4736 volt and the current having the value of 0.0126 ampere per centimeter square. By putting the value of IMP and the BMP, we will find out the value of maximum power. The maximum power is 0.0564 watt per centimeter square. To find out the value of fill factor, you have to divide the maximum power with the short circuit current and open circuit voltage. By dividing them, you can find out the value of fill factor is approximately 87.86% as mentioned in the table. If you know the input power, you can find out the efficiency. The maximum power is 0.0564 watt per centimeter square divided by the input power. You can find out the efficiency easily. The efficiency of the quad junction solar cell is increased up to 41.69%. And the last one is the recommendation for the future researcher. There are multiple areas that can be explored in future research. This presentation focused on the development of a solar cell model that emphasizes the use of optical constant, reflection and extinction coefficient NNK. The model used default setting for other parameters such as permittivity, affinity, radiative recombination rate, electron and hole lifetimes, electron and hole density of state and lattice constant. Additionally, the inclusion of tunnel junctions in the simulation is of great value. One more recommended path is to optimize the physical parameter of the solar cell. The thickness of each of the layer can be optimized to produce better efficiency. I have taken the same thickness and same doping for all of the solar junction cell. The band gap distribution for a quad junction solar cell can be improved to obtain higher efficiency. It should be noted that obtaining the correct optical data for these band gap is essential. Let's start with the simulation. The code for the quad junction indium gallium nitride solar cell was broken down into the 4 single junction solar cell. This was done because the material properties of indium gallium nitride had to be changed for each of the junction. And the top junction having the electron band gap of 2.66 electron volt, and the second junction having the electron band gap of 1.6 electron volt, and the third junction having the band gap of 1.31 electron volt, and the last bottom junction having the band gap of 1.11 electron volt. I will show you the code of the top junction having the band gap 2.66 electron volt. If you want to run for the other, you have to simply change the electron band gap value. You can find out the characteristic curve of all the top junction. You can find out the value of individual characteristics as well as combined characteristics of quad junction solar cell. Let's go to the code. This is my code for the top junction solar cell having the band gap of 2.66 electron volt. If you are the beginner, you must know how to write code of solar cell in Silvaco TACD tool. I will explain you how to write code of solar cell in Silvaco TACD tool. Let's go to the presentation again. A brief structure description of the actual input file follows. First, we have to define the constant. For the ease of changing various cell parameters, the input file lists cell constant as the first line of the code. In future, when we are using this constant, you have to apply $sign to notify the program that it was previously defined. An example is shown below. I have defined the cell width as a constant with the statement set having the value of 5e plus 002 and another constant DIBS division into 1e plus 001. If I am finding the another constant cell width division, I am using the previously defined parameter with the proceeding of $sign. Divide by $sign with division. In this example, two constants are being defined, cell width and divisions. These definitions are then used to calculate the new constant, cell width division, for later use in defining the spacing in the mesh. I have defined the constant with the set statement, cell width, cap width, percent, division, thickness, cap thickness, window thickness, window DOP, emitter thickness. Next, I have defined the emitter doping with set statement MEMIT DOP 10 raised to the power 16, base thickness 3.19467. Next, I have defined some other parameter, base doping, base thickness by BSF thick, BSF dop, cell width. I am using the previous defined constant with the $sign, cell width. These are the different constants. You can note down very carefully to run this program in your PC. Other parameter, emitter base, doping, length, thickness. I have defined everything. Then the window low, window high, window division, cap low, cap high. Some parameters are used for defining meshing. Next, I have defined some other parameter with the help of set statement. Next, I have started the meshing. The mesh width with the width 3D X meshing. I am using the variable parameter cell width half with the spacing cell width division. This is the X meshing. This is the Y meshing. After defining the constant, we have to define the meshing. The mesh is specified onto which the device will be constructed. For this program, the mesh was defined using the Atlas command language. The commands generate a grid lines area used to define data points and solution points, similar to a finite element solution. 2 or 3 dimensional figures can be constructed comprised of many different sections. Please note that there are 2 important points about the mesh. First one is that the dimensions are in micron. and the second is that the vertical mesh is negative in order to build the solar cell above the surface of the device. The negative dimension is needed since the software interprets the position as a function of the depth below the surface. The positive number would build the solar cell down into the device while building. It is on the top of the device. Rectangular or cylindrical coordinate system can be used when defining the mesh. Constants can be defined as stated above for ease in defining and altering the mesh. Atlas automatically adjusts the grid line spacing to match the desired value. The number of triangles in the mesh determines the resolution of the simulation. The density of the triangles is an important part of the simulation. If the density is too high, then the execution time rises significantly without adding much to the resolution. If the density is too small, then the resolution is poor, leading to an inaccurate or incorrect simulation. So we have to make a balance between the coarse meshing and fine meshing. One point here is to note that the vertical meshing is negative in order to build the solar cell above the surface of the source. You can note down in the meshing in the code, you will note down that the vertical meshing is a negative value. After defining the mesh, you have to define the region. Next, material region need to be specified. All parts of the mesh are assigned material names. There are 6 regions defined. The limit of each region are explicitly identified in the X and Y axis. The region must then be given to a material. In this example, we are using the 6 material. The material number 1 is indium gallium nitride arsenide. Second is vacuum. Third is vacuum. Fourth is indium gallium nitride arsenide. And the fifth one is the indium gallium nitride arsenide. I have taken, this is for the example. In the code, I am using indium gallium nitride. Let's go to the code. I have defined the meshing X and Y. Please note down every point very carefully. After defining the meshing, you have to define the region. I am using the 7 region statement. Region number 1 is for the indium gallium nitride, having the parameter value X minimum, X maximum, Y minimum and Y maximum. And the region number 2 is vacuum. Region number 3 is again vacuum with their positional parameter. Region number 4 is indium gallium nitride. Region number 5 is again having the indium gallium nitride, and the region number 6 and 7 having the same indium gallium nitride material but having the different positional parameter. Note down the every region very carefully. We define the 7 region. After region, I have defined the electrode statement. In electrode statement, electrical contacts must be specified in the atlas structure to obtain the electrical properties. Electrodes can be either defined as a specific material or atlas uses a perfect conductor at the specified location. You don't need to mention the electrode name. If you don't mention the electrode name, then the atlas will automatically choose a perfect conductor for this location. Typically in this simulation, the only electrode defined are the anode and the cathode. Note down the cathode is defined with gold as the material on the top. Meanwhile, the anode is defined at the bottom of the cell for the entire X range at Y is equal to 0. This way. I have defined the 2 electrode, cathode at the top and the anode at the bottom. With the positional parameter, you can note down that after defining the region with material, I had mentioned that the electrode statement. Electrode name is cathode, material is gold, with their positional parameter. Then the electrode name is anode with their positional parameter. Two electrodes I am using in this code, cathode and anode. After defining the electrode statement, you have to define the doping. Each region with a semiconductor material is allocated a type and level of doping concentration. Doping can either be N-type or P-type with the choice of uniform, linear or Gaussian distribution. The concentration is in units of impurity per cubic centimeter. For example, for the region number 1, 4 and 5, I am using the doping of 2E18, 1E20 and 8E18. After defining the electrode statement, you have to define the doping. Doping for indium gallium nitride cell, not phosphide. Doping uniform, region number 1, N-type, concentration, cap doping, window doping, emitter doping, base doping, and BSF doping. I have defined 5 doping regions, 1, 4, 5, 6 and 7 with different doping. After defining the doping, you have to define the material. You can define the new material. A library of material is a part of the Atlas tool. Many common material can be selected from the library for use in defining material properties. Since solar cells are using state-of-the-art materials that may not be listed in the library, Atlas has the ability to fully define new materials. A minimum set of property data must be specified for a new material to include band gap, dielectric constant, electron affinity, densities of conduction and valence states, mobilities, recombination coefficient, and an optical file containing reflective indices and an extrinsic coefficient K for a material. The optical file determines the transmission and attenuation of light as it passes through the semiconductor. Various other parameters can be defined with the material statement. Example of these parameters are the band gap at room temperature, electron mobility, electron and hole recombination, lifetime, TAU and 0 and TAUP syntax is used, conduction band density at room temperature, among others. After defining the doping, I have defined the material statement. Material properties, opaque contact. First material I have defined with the material number region 2, index file, vacuum, indium gallium arsenide with a mole fraction of 0.20, and the material for the region 3 having the same index file. Next, I have defined the some property of the indium gallium nitride material have the electron band gap and in the index file which contain the wavelength, index of reflection of proposed material. Next, I have defined the gold material with real index 1.2 and the imaginary index 1.8. After defining the new material statement, I have defined the different model used in the solar cell. Atlas can use many different models in a device simulation. These models can be defined for particular regions or over the entire device. The optical recombination model was used extensively throughout the simulation along with the concentration dependent mobility model. The concentration mobility model CON-MOB adjusts the electron and hole mobilities according to the dopant concentration. The optical recombination model OPTR determines the possibility that a photon is generated when an electron and hole recombine. Next, green has shown that the OPTR, not OTPR model increase the accuracy of the solar cell simulation. After reviewing Canfield's thesis and the Atlas user manual, the band gap narrowing model was added to the model list. BGN along with the device is used for the device temperature take into account temperature dependent band gap narrowing. I am using the different model for the reason 1 concentration mobility model, and the different models CHUANG Chong model for the concentration mobility, field mobility, SRH. One more is OPTR model and the print model. These are the 6 models you can use in designing of a solar cell. Please note down this model very carefully. Next, you have to define the light statement. Atlas Luminous Optical Electric Simulation Module has the ability to determine photo generation at each mesh point. Thus, a number of light sources can be simulated with the various changes in the location, orientation, and the intensity. Based on the Atlas user manual, Bates, one of the researchers, explained it in very simple terms as follows. The refractive index N is used by the luminous to perform an optical ray trace in the device. Differences in N value across material boundaries determine the rate of light transmission and reflection. By following the path of the light from the source to a mesh point, luminous is able to determine the optical intensity at that point. The extrinsic coefficient K is used to determine the rate of absorption and photogeneration. For the calculated optical intensity at each mesh point. How we define light in the code, I will explain with the help of code. I have defined the beam number 1. X origin 0. Y origin is the light Y. Angle 90. Back dot reflection. Power dot file AM node air mass is 0. NREL dot SPC slash wavelength start from 0.12 micron and end at wavelength 2.4 micron with a sample of size of 50. Next, you have to save the structure file. I have saved the structure file with the name of single cell underscore W. You can use any of the name to save the structure file. After, you have to give biasing voltage to the different points. I am using the method statement Gumail, Newton, maximum trap 10 and IT limit. Maximum trap will reduce the convergence problem. I will explain in my previous videos. If you don't know about these two commands, you can follow my previous videos. First, I will solve for the beam 1 having the light and intensity of 0.9. I am using the two beam ray, one having the intensity of light is 0.9 and other has 0.95 with different method statement. Now extract the short circuit current. For the short circuit current, you have to set the different value ISC, IN1, IN up to I25. You can note down these values to find it. This will be used for the extract command. Next, you have to find out the log file. We have set the different value for the I1 to I25. Next, I am using the solve statement to find out the anode current. For understand the solve statement, after defining all the input parameters, Atlas can use various methods to solve for the output data. Various numerical methods can be used to solve the cell parameter. Perform a solution for one or more bias point. The following is an example of the solve statement. Solve beam 1, beam 3. We are using the two beam 0.9 and 0.95 intensity. That is the beam 1. We can use the SS photo, SS.light 0.01, multi.frequency, F step and F step. If you don't know about that, you can follow the Atlas manual. V1 and V3 specify the optical spot power associated with the optical beam 1 and 3 respectively. The beam number is an integer between 1 and 10. Beam is the beam number of the optical beam during AC photo generation analysis. SS.photo is the small signal AC analysis. SS.light is the intensity of the small signal part of the optical beam during signal AC photo generation analysis. Mult.f is the frequency to be multiplied by f step. Nf steps is the number of times that the frequency is incremented by f steps. I have saved using log statement. Next, I have used again the method statement and the solve beam 1 for 0.95, contact name, anode current. Simply we have to find out the anode current at different point. I have taken 25 points to solve anode current. You can use any, you can use 20, 10 also. After solving the anode current at different point, logo, you can extract the IV characteristics, voltage at anode and the current at cathode with the out-of statement, Tony plot, this dat statement and the final log file. If you want to run for the same program for other junction, you have to simply change the band gap of indium gallium nitride material and the mole fraction. If you run this program, you will get the structure file and the log file. If you did not note down the code, note down every step very carefully. I will show it up to set emitter. Please note down very carefully. This is the X meshing, Y meshing. This is the reason statement from 1 to 7. Next is the electrode statement. I am using only two electrode, cathode and anode. Next is the doping statement. Next, I have defined new materials region with different optical index file. I have defined the material gold and indium gallium nitride with some properties. Different model I am using. This is the light ray statement I am using. After that, you can save the structure file. You will get the structure file. If you want to log file, you have to apply voltage to the device. Use solve initial statement. I have found out the anode current for 25 different value. I have sent the different point. Next, I am using the log statement method. I am run the program for the beam 1 4.95 intensity, contact name, anode current, method. This is the solve statement for the different node point. Now you have to extract the log file. When you run this program, you will get the structure file and log file. This is the structure file you will get after run this program. This is the indium gallium nitride material. Yellow one is the vacuum region. And the aluminum gallium arsenide. If you are zooming this point, you will get the aluminum gallium nitride material. I'm using gold as a cathode material. I'm using conductor, this one, and I'm using the electrode at this point, cathode and the anode. This is the log file you will get when you run the program for the indium gallium nitride. The open circuit voltage is approximate 5 volt and the short circuit current is about 0.013 ampere per centimeter cube. This is a cathode current. My dear friend, this is end for today. If you like my video, please subscribe my channel and share my video as much